of our week. To me, was a wonderful week, and I'm very happy to be here and be able to talk to you, and maybe, hopefully, to you a little bit more of information related certainly to the work you are doing, to some future work you are pretending to do. Okay. Now, today I'm going to talk about optical spectroscopy. Though yesterday I already presented Raman spectroscopy, which is all spectroscopy. But today the focus will be more on absorption and luminescence. So my presentation this morning maybe will be the shortest one, but I hope I can include enough material to give you some idea of typical experiments. Usually they are taken together, absorption and luminescence. So luminescence, you might ask, you might call luminescence like photoluminescence or fluorescence or phosphorescence. It's the same. The difference is the lifetime of the. So typically photoluminescence is on around nanoseconds in the excited state. Fluorescence is 3 orders of magnitude higher, microsecond. And phosphorescence is again 3 orders of magnitude higher, millisecond. So this is the difference actually, basically. The background is about the same. The physics is about the same. Okay? Optical spectrometer. It is the same. I presented to you yesterday for Raman spectroscopy. So we don't change spectrometer to do luminescence or just the same. You have to be careful, of course, to drive source of light, a laser. That's all. These days, most of the absorption, especially absorption spectrometer, the source of light is a lamp, a bulb, because it's easy to extract wavelength in a wide range. But also you can use tunable lasers, like dye lasers, to scan in a wide range of wavelength. So you can eventually, if you are working not in such a wide range of wavelengths, you can do that using lamps. But if you are working in a more narrow range of wavelengths, you can use dye lasers because it is able to scan in a range. So then basically the optics is the same. And today many of the commercial equipments came equipped in a way that you can perform ultraviolet, visible, and near infrared range, all this range. That obviously you cannot cover this with a single laser. Now wait, you can cover fractions of it with laser. For instance, with dye lasers, you can cover range on the visible range, for instance. With titanium sapphire laser, you can cover the near infrared. But all these lasers, you can change the wavelength. Actually, behind that laser, it is another laser, the pumping laser. So, if you need to work with lasers to perform absorption or excitation spectroscopy, certainly your facility is going to be much more expensive. Maybe just the pumping laser like argon laser and a dye laser all together, the two pieces, only optical source, maybe cost you more than the full equipment like this. So, but you know, it depends on what the goals are, how sensitive, what is the sensitivity you need to work. Okay, so most of the data today, people are taking on those commercial spectrometer without no problem. Okay, let's try to cover this agenda, which is not too long, and mostly I'll try to focus on semiconductor structures. This is the focus today. But almost everything that I'm going to talk here also applies to molecules. If you do optical spectroscopy of molecules, it's about not too different. Even experimental data is not too different. Okay, so again, this is a typical setup, experimental setup of a spectrometer, optical spectrometer. As you can see here, you have your light source, then it comes to a monochromator. So allows you to scan over wavelength. And then from the monochromator, you take the light, the beam, the optical beam, and then you probe your sample. Once you probe your sample, you can extract your spectra. Okay? So all your spectra is extracting from here. Of course, there is a processing and everything. There is reference over there, but this is a typical arrangement, very typical. And similar to Raman spectroscopy. So if you look here in this case, if you are performing Raman measurements, you are in the configuration of forward Raman. Also, we do backscattering Raman. So there are different configurations, but they are very much similar to one another. And inside the monochromator, what happens is you have the entrance is lit here, where the light from the source just coming in. It bounces around in some mirrors, but it goes to a grating, just to opens up the spectrum. And then it goes outside in this exit slit, and then that's the light you take to your sample. Okay, so saying this, we can look at the data and how the data come from. You know, there is a basically the system is split in two bands. You have the valence band down there and conduction band up there. This is a typical physics approach for understanding the energy levels in a solid. If the difference in energy between conduction band and valence band is what we call the band gap. If this band gap is very short, And then if the two bands starts to overlap, and then you have a metal. So if these two bands increases and they are taken far apart, you have some insulating. That's the difference between metallic behavior, semiconductor behavior, and insulating behavior. If you change your material, actually what you can do band gap engineering. You can modulate this gap. This is possible. Nano structure, what we did actually, the effective band gap, we call effective band gap. We can modulate the effective band gap. Let's say the bulk material has this band gap, like silicon. And then you fabricate a very small particle of silicon. The effective band gap is not like this much anymore, it's higher. And as you squeeze the size of this silicon nanomaterial, it goes higher and higher. So it is a way to modulate the effective band gap. It's what we call band gap engineering. You can do this with all semiconductor materials. You can fabricate nano semiconductors. Then you can modulate the gap. But when you do this, you get to a new sort of basic physics. It is not exactly like this one anymore. This is a typical of bulk materials. And just to remind you, so here is the situation that takes place when you illuminated your semiconductor. If you illuminated your semiconductor, what happens is you just promote one electron from the valence band to the conduction band. So electron goes from here to there. And then it wants to get back from the excited state to the ground state. When it has this transition, it just emits the photon. On the other way, if you illuminated your material, eventually you are going to make this transition. So your system absorbs a photon, and then there is a transition from the ground to excited state. But eventually that excited states that carry electron in the excited states in the conduction band, that guy is not going to survive there forever. Between picoseconds or nanoseconds and milliseconds, eventually this excited electron does come down. Experimentally, when you take your sample and illuminate your sample with wavelength, changing wavelength, what you are doing is promoting electrons from the conduction band, from the valence band to the conduction band. This is absorption. As I said, eventually those guys up there, in the excited states, they come back to the ground state. If you collect this light emitted, you are doing luminescence. So somehow absorption and luminescence are cycling and sort of opposite. If you look at the spectra, you always can match absorption and emission spectra. But usually they don't match exactly, because there is one effect which drives these two spectra to be far apart. We will see this. So, what happens if you take a bulk material and make that book material nano-sized. Okay? So before I get to this point, let me remind you a very simple physics here. Very basic quantum physics. Let's say you have a particle and has mass and linear moment p and mass m. And so you see this axis is potential energy. If this particle has a linear momentum, it means it has some velocity. But according to this plot, this is potential energy. Eventually, this is zero, which means this particle has, besides kinetic energy, it has also potential energy. And that is much, the potential energy. So this particle has not only kinetic energy, which is this one, but also potential energy, which is this one. So the total energy is this. But if this particle faces a barrier like this, a barrier like that high, so this is potential energy of the barrier. If this potential energy is higher than the potential energy of the nanoparticle, of this particle, it doesn't cross. Just kick there and go back, right? Reflex. And by linear moment conservation, the moment backwards is just the same, just opposite. There with p and go back with minus p. Okay? Doesn't cross the barrier. This is the classical view. But let's say what happens if the mass of this particle just shrinks in very small. Then the physics changes. So for very small particles, physics is not good anymore. We need quantum physics. And equation for one particle is this one. That's Schrödinger equation. It tells you, see, the mass, it appears over here. If the mass is so small, this fraction, you might guess, is so huge. Wow. But there is somebody over there. The Planck's constant, which is very small too. So Planck's constant is even very, very small. So this term is important for small particles. And actually this term describes kinetic energy. We can understand, of course, this is the classical linear momentum, and this is the quantum linear momentum. If you take this guy square like we take here, to calculate kinetic energy from the classical point of view, just taking this square over 2m. If you take this operator square over 2m, you get exactly this guy. So this equation is nothing else than kinetic energy plus potential energy is the total energy. Only this. Wow, it looks so easy to extract the Schrödinger equation, right? But the point is how to figure that quantum linear momentum is given by this. That's all. That was not easy. The guy who published this is, his name was Schrödinger. He was a professor in University of Vienna. And his whole life, and he won the Nobel Prize. His whole life, guess how I published? 6. It's not the number of papers which matters. This is a very interesting lesson to all of us. It's how important the work is. So, what was the impact of quantum mechanics in science, in our life? Amazing. And this is just the beginning. So quantum mechanics came and gave to physics a new, completely new world. It makes a big revolution in chemistry. Chemistry is quantum mechanics plus statistical mechanics. That's all. Now, quantum mechanics is performing a huge transformation in biology. Maybe in medicine. So, this equation. Actually, before this equation, of course, it was the work of a young guy called French. So Louis de Broglie was the guy who, in his PhD thesis, he wrote a connection between particle and wave. It was his PhD thesis. And Louis de Broglie was not a student in the physics department, the history department. But his brother was in the physics. And he used to look at the books of his brother and said, wow, this is amazing. It looks much better than history. I'm going to switch. He did it. Well, okay, let's move. So let's take this experience here and make this barrier a little bit complex. Like this. With the same particle, very small, and then instead of just one barrier, let's build two barriers side by side, but one gap in between. This is called quantum well. It is in almost every quantum physics book, first level. I think I learned this in 1976. Now, what happened is, this particle, in terms of classical physics, it should kick here and go back. But in quantum physics, it's different. Once this particle hits this wall, it has probability to get inside. It goes inside. If you have an instrument to measure this particle, and if you perform this experiment, this instrument will tell you that the number of particles in this region is not zero. There is a probability to come here, but if the particle comes inside, it is not allowed to have any. No. Energy inside the well are quantized. Particle can sit only in a well-defined energy levels. And moreover, if you squeeze this gap, shrink in, all energy levels goes up in energy. If you make it wider, all energy levels goes down. If eventually you make it so, those will collapse. And then, that's the book. That's the book. That's the book. So, what nanoscience does is just to take the book, shrink in, make a quantum well like this, and then the energy levels just split. And those energy levels you can populate. So, this particle, you can think about electrons or holes. And we can describe this particle using a very important concept called effective mass. This is an amazing concept. Effective mass, it says, electron in a free has the free electron mass. 1.6 times 2 minus 19 grams, something like this, nearby this. So, but if you take this electron and put in a solid, now electron will interact with all atoms in the solid. But this interaction is not trivial to describe. If you want to describe the interaction of one electron inside a solid, it means the interaction of this electron with all atoms in the solid is very complicated. It is possible, but complicated. But then people found a way to get around the whole trouble. They transfer all the complexity of this interaction to the mass of the electron. And then you can say something, well, instead of describing all the complexity of interaction between electron and atoms in the solid, let's say this interaction is in such a way that it changes the electron, making it higher or lower. And then you build this concept of effective mass. Amazing. Once you this concept, then you can solve the Schrödinger equation using not the free electron mass, but the effective mass. More important, you can measure the effective mass in the lab. You can perform simple experiments and measure the effective mass. So it's a very important concept, and indeed you can measure that one. So once you measure the effective mass of electron in any kind of material, then you can perform all band gap engineering using that effective mass and solving this equation. So how you can fabricate this in real life? Yeah, you can do it. Let's say you can fabricate layers of semiconductor. Let's say you take a substrate and make a deposit of one semiconductor with wide band gap. You stop growing that and start growing a layer with narrow. And then you stop that and grow a layer gap again. You make this. Unfortunately, this TEM is not very much good for today. Because when I took this in 1987, it was so good. At that time, 20 years ago, exactly. It was about this time, by the end of the year. I was working at Bell Labs. So this was the best instrumentation you can have at that time. And you can see here, you have one phase A, one phase B, and another phase B. The phase A was a thin layer of indium gallium arsenide, band gap. And the barriers we call barriers, which is B, is indium phosphide, wider band. And this layer here, at that time, we managed to have just one atom. One single atom. It was a huge breakthrough at that time. That's why they want me. And I just ran back to Brazil. Okay. Now, we managed to do this. And then you can calculate. It's not very hard to calculate these energy levels. Not very hard, I can tell you. Solution of Schrödinger equation, even for the barrier, not infinite barrier, but finite barrier. It doesn't give. Calculate this, and then you can extract the energy levels. Once you have the energy levels, you can calculate the energy transition between each of levels of the conduction band with respect to each level of the wow. And oh, Bailey's band, sorry. So you can calculate easily. Once you can calculate this, if you build a structure like this, you fabricate a structure like this, you can look at this spectrum. And what you see is something like this. This is the real photoluminescence spectra of different samples with different thickness of the quantum well. And this is experimentally. So you can see those peaks, like this one. This is a peak. You can extract this peak position in wavelength and transform that in energy. And the same you can do it with this peak. Again with this one, this one. This sample is a little bit thinner. Sample A is a little bit thicker. But you can see clearly that this peak matches this shoulder. This shoulder matches that peak. You know why? Because your sample, this kind of sample, has regions where there are only 2 atom layers. Some other regions are 3 atom layers. Other are 4 atom layers. So this sample is not uniform in thickness in a huge area. I was able to scan the laser spot around the sample and collect regions where you had 2 atoms layers, 3 atoms layers, 4 atoms layers, and took the spectrum. And here is the calculation. If you see here is the energy. What is that one? Okay. Peak position. So you can see the symbols are experimental data extracted from sample A and sample B. And the solid line is exactly the calculation from the previous equation, Schrödinger equation. I can tell you, the day I took this, and the coming days, 2, 3, 4 days after I got this data, though I had learned about Schrödinger equation 10 years before I took this data. So 10 years before I took my first quantum physics course, it was a time I heard about Schrödinger equation. 10 years later, I took this data. When I took this data, I told myself, it works. Indeed, it's not only, math. It really works. Amazing how precisely it works. That was I convinced myself quantum physics really exists. It's not only manipulation. Okay. Now, what happens if you take this structure and put not only one electron inside? Let's take the second, the third. Let's take many electrons inside. What happened to this structure if you take many electrons inside? So you can see here the band edge is flat, right? But if you take too many electrons inside, it is not flat anymore. It is like this. It bends. Why it bends? Because this bend is a potential, electric potential. And if you take any charge near any potential, that charge just modifies the potential. We know this is called Poisson's equation. Simply like this. So the Poisson you, if you take a charge, then you just bend potential. The derivative of this potential is exactly the density of charge. This is called Poisson's equation. So, because we took many electrons inside, then comes the Poisson equation, just bend it. It's called band bending. But once you put electrons inside, you left the region outside without electrons, which means you have positive charge outside. In physics of semiconductor, we call this accumulation layer. So, if you have positive charge outside, again the Poisson equation makes this potential to bend. It's not flat anymore like before, it bends too. So all the band bending you can see here is credited to Poisson's equation. But, so this bending here also, it shifts the energy levels. Besides this, when you accumulate charge in a same point in a semiconductor, it also shrinks in the gap. It's called normalization. That's the word. Because of the band bending and the band gap renormalization, the energy levels just move around. Besides, if you put electrons inside, then there is a difference in energy between the top of this electron charge density and the bottom. And you know that the top of that charge distribution is called Fermi level. Right? Okay. So, if you keep this picture in your mind, you can understand absorption and emission spectrum. This is all you need to keep in mind. This is the basic physics to understand absorption and emission spectroscopy in semiconductor nanomaterials. That's all. Okay, once we have this in mind, and then here again is the Schrödinger equation, the same. Only here you have the effective potential, and the effective potential now is the initial potential plus some extra potential. This extra potential is called R3 potential. And the R3 potential comes from the band bending and band gap renormalization. Typically, the energy shift provided by the band bending scales linearly with the charge density. And the shift in energy provided by the R3 scales with 1/3 of the charge density. That's band gap renormalization. So the first term comes from the band bending, and the second term comes from band gap renormalization. This is valid for any nanomaterial. And the density here, the charge density, it could be not only electrons, but could be holes too. Electrons in p in n-doped semiconductor and holes in conductors. So if you are working with, metal oxide nanoparticles, semiconductor metal oxide nanoparticles, like tin oxide, then this equation should apply. And then this is the basics to understand the absorption and emission from those materials. Okay, now look at this paper, recent, last year. What they did, they fabricate small dots of silicon. Small. How small? 2 to 3 nanometers in diameter. And they were able to measure luminescence of each one by one. And this is a picture of luminescence. So those are each spot like this, which looks like stars. Spot like this is just one single dot. And here you can see the PL on the left hand side. This is energy increasing this way increasing. This is the PL taken from this. The dot points, the red dot points are experimental. And this is the absorption spectrum. And you can see the absorption spectrum has some visible 3 shoulders, which are 3 levels of energy. So this is PL on the left hand side and absorption on the right hand side. Same material. But you can see luminescence comes at lower energy and absorption comes to higher energy. The difference between the peak position of PL and the first peak of absorption, this distance, is called Stokes Shift. This is the Stokes Shift. And roughly, in this case, in case of nanomaterials, especially semiconductor, the Stokes Shift comes because of this. So this quantum dot, it has charge inside. So I'm going to write like this. Bending. There is a band bending. And here, this is the conduction band, and this is the valence band. See? You draw like this. And then you have levels here in the conduction, in the valence band. Usually light hole and heavy hole, right? And then you have energy levels here, electron levels. But there is no color. Okay. But then here's the first level. This guy might have some, not only one electron inside the dot, but more than one. Actually, a gas of electrons. So the gas of electrons is over here. That's the bottom, and here is the Fermi level. So this is E1, E2, E3, the energy levels. That transition, the PL transition, likely is the transition from the bottom to here. And the first absorption is the absorption from this light hole to the top of the first band, to the Fermi level, because electron cannot come to the bottom. It is occupied. So it has to go to the top of the firm level. So this difference in energy scales with the charge density here inside. This is called Stokes shift. So in semiconductor quantum dots, no matter what the shape is, this is the case. Of course, if your system, if your sample is n-doped, if that is p-doped, then what you have is a density of holes down there in the light hole. But you can see the same in the spectra. And PL and absorption, you see exactly the same.
So the PL occur from bottom of the conduction band and not anywhere else?
The bottom.
Bottom.
Always from the bottom. PL comes always from the bottom of the first level. Eventually, you might have transition PL from maybe from the second or from the bottom to the second level in the conduction in the valence band eventually. But if you look at the matrix elements of those transitions, the strongest one is from the bottom of the higher level to the top of the lower level. That's the most likely. And that's usually what you can see experimentally. Okay. So here you can see the same sample but different temperatures. 300K room, and you can see the PL line, it's quite broad. Look at that. About 90 millielectrons volt in line width. If you lower the temperature, then it comes very sharp, 5 millielectron volts. PL, if you want to get very good information about energy levels, you better lower the temperature. The best way is to take your sample, put inside a cryostat, liquid helium. Pump your liquid helium, which is at 4.2 K, and then you pump it, mechanical pump, big one. And then you lower the temperature down to 2K, which is, and then when you do this, the liquid helium comes to a phase transition to a super cold state, and then it's very quiet. You can do optics, right? So if you don't do this, you cannot perform any optics if your sample is immersed in liquid helium above 2K. So if you pump the helium, it goes to a superfluid state. In the superfluid state, it's just quiet. Nothing, no bubble, nothing. You can look at the window and see the phase transition of liquid helium from the liquid state to the superfluid state. So it's about 2K, 1.8K. But remember, yesterday I mentioned to you, don't do this with Raman spectroscopy. So Raman spectroscopy, you better perform it at room temperature. Okay? It's no cost. But luminescence, you better lower the temperature. The lower you go, the higher the signal, and the better the resolution. But this is typical. In this paper, they calculate the absorption band, and then you can see the solid line is the calculation. Very good. And the three energy levels here, you can see the components here, the convolution of the spectrum in three components, three levels. They managed to probe three levels. Okay, now is another paper. In this case, we fabricated. maybe less, no, 2014. I guess, yeah. Yeah, 2014. ACS Nano. Okay. Then you can see what we fabricated here was a sort of core shell nanoparticle. The core is cadmium selenide. The shell is cadmium sulfide. Cadmium sulfate. But in between the two, there is a transition region. It's an alloy, actually. So the core is pure cadmium selenide. The shell is pure cadmium sulfate. But in between, they mix together. We were able to track this. And then a very important point here were the PL and absorption spectrum. So the way we synthesize this material, and then you can see the gap. Cadmium sulfate has a wider gap, cadmium selenide a narrow gap, and then we can build quantum well like this. But the guy here in between has a gap in between cadmium sulfate and cadmium selenide, which is alloying. It depends how wide the gap is. It depends on the composition, the X composition. Okay? Now, we synthesized this material in different conditions, so we managed to change the size of the core. If you change the size of the core just shrinks in, energy levels goes up, and then you might see this in the absorption and also in the PL. And we did. If you look here, so this is the first absorption, and then you can see the absorption just moving, different positions. Likewise, you can see the PL line moving. So here's the first PL line, so it moves a little bit, moves more, moves a little bit more, which means this sample is smaller. That's the smallest one. So we imagine it to modulate the size precisely. So that's what we say, shell thickness modulation. So we manage to modulate not only the size of the core, but also the size of the shell. The optical properties of this material can scan in array. At the end, you may say, okay, I can fabricate those nanoparticles with emitting different colors. It might have some application. I don't know. But it doesn't matter whether this is going to have some application in the future or not. What matters is we enjoy doing this. Okay, now another one. This is from well, I don't know. So small here. Oh, last year, 2016. Okay. Now, in this case, we also made a similar research with cadmium selenide and cadmium sulfate again, but using a different approach of synthesis. In this case, we observe that still there is a layer in between the core and the shell, but this layer now is much thinner. We managed to reduce, which means the interface between the core and the shell, in this case, is sharper. So we learn how to modulate this interface. Not only the core, the shell, but also the interface. We could probe all these samples, we could probe using absorption and photoluminescence. Very important techniques to check this. Well, finally, this one is a different system, is zinc telluride, also typical semiconductor. Again, they were fabricated changing the size of the nanoparticle. And it comes from the same system. So you have a quantum dot, and then you have a quantum confinement. If you change the size, the energy levels just move up and down. And you can fit the data using equation like this. Not very complicated equation. This is an approximation. If you, in your experiment, in your optical experiment, if you pump hard the laser you are using, what you do is that you generate a lot of carriers, electrons and holes. And then once you generate a lot of carriers, this effect becomes very important. And so this equation is not valid anymore, because this equation is supposed to be equation for a single particle. You excite your sample with high intensity in the laser. What you do is that you generate a lot of carriers inside the dot. And the density now is high. And then you need to take into account the effects I mentioned to you, the band bending and the band gap renormalization. And at the end of the day, the equation is much more complicated than this. So when you do this kind of experiment, usually we use as low as possible the optical intensity to illuminate, just to avoid this kind of effect, and make easier to you to analyze the data using a very simple approximation, which is worth to use. Okay, so I told you today is going to be a short, maybe the shortest one, but even the shortest one run for almost 1 hour. I have a last picture to show you. This one. Guess what is this? Do you think it is a surface electron microscopy or something like this? Huh? Not really. Not really. Can you guess what this is? This is the map of my city. This is the capital of Brazil, Brasilia. So, let me show you some details. I want to introduce you my city. Here, the city runs from here to here. This is the south wing, and this is the north wing. The city was the second city planned in Brazil. The first planned city in Brazil was the capital of my state. It was planned at beginning of the 19th century. This one was planned in the middle of 20th century. It started in 1960. This city looks like this. This is the south wing, and this is the north wing. And you can guess from the picture, it is a body over here. It's like this, the city. This is a bird. This is the north wing of the bird. This is the head of the bird. This is south wing. And this bird was born in the west. But this bird is flying to the east. Full of meanings, this city. Here in the head, is the presidential office. It's here. And here, just nearby, is the parliament. And the parliament building looks like this. Two buildings side by side, and a connection between the two, a corridor connecting the two sides. One side, there is a big room like this. The other side, a big room like that. One facing down, another one facing up. This one is the representative chamber. And this one is senator chamber. The representative chamber is hearing the ground, the people. And the Senate chamber is hearing the heaven. That's the meaning. This H is because men in Portuguese, the word men in Portuguese is this. That H comes from this. And here, in this bird, here is our cathedral. This cathedral has a shape like this. Because when you pray, you put the hands like this. That's the way it looks. So, from here to here, 16 kilometers. You drive all the way through, no lights. There is not a single light. And from here you come straight to the airport. The airport is right here. Very easily to get the airport, very quickly. The university is here. You can see we have a lake. This is the lake. See? This is the lake around the city. You can see a peninsula here, right? Looks like Italy. See? My house is here. Exactly at the beginning of this peninsula. Okay. We have some bridges. The newest bridge is crossing this point. There is another bridge over here. There is another bridge to go my home over there. And there is another bridge to go to the airport. Here is the airport. Here is the airport. Runway. Okay. Roughly, this is the city. The city is so well planned. Schools can only be built in some specific areas. Hospitals, the same. The university is here, nearby the lake. The buildings, residential buildings, cannot be higher than 6 floors. In the center of this bird is the bus central station, local bus central station. Just as you cross from south to north wing, just after you cross the bus central station, on the right hand side is the National Theater. Now I'm going to fly you from nearby the new bridge here, Then we are going to fly the lake, see the second bridge. We are going to fly here and enter the south wing and fly all over the bird. From south wing to the north wing, cross the bridge where I use every day to go home. From my home to sea. So remember, from here to here is 16 kilometers. From my home to the university driving, I take no more than 10 minutes. Safely. Safely. Okay, now I'm going to show you the video. Is there the video? So this is the way I want to finish my lectures. Is the sound in?
Sound in.
Okay. All right. Yeah, this one.